Okay, so this is a continuation of section 4 too. So this is day 2, and we were talking about the antiderivative and this idea of finding a function from its derivative. And so that is we're going to talk a lot about this in second semester, but we're just scratching the surface in this section today. And so when we do this process of finding the original function, knowing the derivative, we call this the antiderivative because it's the reversal of differentiation. And so a lot of times what we do then is we say we distinguish between the function and its derivative just by capitalizing the f in the function notation. So typically when we use a big F, we were referring to the function almost like a parent function, I guess you could say. And then the derivative is little f. So we kind of read this antiderivative definition as the following. A function big F of x is the antiderivative of a function little f of x if we take the function big F and differentiate it, and we get function little f. And so that process is called finding the antiderivative, or we sometimes just call it antidifferentiation. So, like I said, you'll hear a lot more about this second semester. This is just an introduction to start kind of setting the foundation, so to speak. So let's try this, and we're going to use this with a motion example because we know the relationships between position, velocity, and acceleration in motion involve taking the derivative of one to get the other. So we know if we start with position and differentiate, we get velocity, and then if we differentiate again, we get acceleration. So we're gonna reverse that process, and we're going to start with acceleration, and we're going to antiderivative to get the velocity, and then we're going to do an antiderivative again to get the position. So we start with the acceleration. The acceleration is 9.8 meters per second downward. So we can say that our acceleration function is negative 9.8, negative meaning down. So we're going to do the antiderivative on this function. So we have to think to ourselves, what function do we start with that gives us negative 9.8 as the derivative? And that's negative 9.8t. So let's just do a quick check. If I take the derivative of negative 9.8t, I get negative 9.8. Okay, but we get a constant of integration with that too. Remember, we could have negative 9.8t plus 7. Or we could have negative 9.8t plus 2, potentially, and still get the same derivative. Well, now we're going to deal with actually finding this plus c. This plus c is what we call an initial condition. So in other words, it's the velocity that we have at the beginning. And in the statement, it says the body falls from rest. So from rest means an initial velocity of 0. So this c is in fact 0. So this velocity function then becomes negative 9.8t. So now we've got one step backwards, getting the velocity, and now we're going to, there's our plus 0 for our initial velocity. And so we don't have to write the plus 0, so there's our velocity function. And now we're going to do the antiderivative again. So now we're going to do what is the function we start with, that when we take the derivative gives us negative 9.8t. So we know we need to start with a t squared, and then we need a number out front that when we bring down the 2 and multiply it gives us negative 9.8. And that number is negative 4.9. So let's just quickly check this. Bring down the 2, multiply it by negative 4.9, we get negative 9.8, and then t, reduce the power. So that's it. Then we have our plus c because we did the antiderivative. And this plus c, notice I used plus c again, and that's okay to use it multiple times. It just represents any random number. But the number isn't really random because the problem here states what the number should be. We are starting from the origin. And so from the origin means an initial starting value of 0. So this is also 0. And so we can call this position function then negative 4.9 t squared. And so we can put in the plus 0 at the end if we want to, but really it just simplifies down to that. And so, so this is our position function, and this is our velocity function when we start at rest and we start from the origin. So now we're going to change this example just a little bit. Instead of starting at rest and starting from the origin, we're going to start with an initial velocity of 1 meter per second up, and we're going to start from 3 meters above the origin. And let's see how it changes the equations. So again, we'll start with our acceleration function, negative 9.8. And we're going to differentiate, or we're going to take the antiderivative, and we're going to get negative 9.8t plus c. But now our initial velocity isn't 0 anymore, it's 1 meter per second upward, which means plus 1. So our velocity function is really negative 9.8t plus 1. And so now we can take the antiderivative again on the negative 9.8t plus 1. Now we can take the antiderivative again to find the position function. So we're going to reverse our derivative rule. We're going to bump our power up to 2. We know this is negative 4.9 here from the other example. But now we have to do the antiderivative for 1. So what did we start with to get a derivative of 1? And we started with 1t. So there's our position function. We have a plus c on the end. And we know that our initial position is 3 meters. So our position function then is that we have negative 4.9t squared plus 1t plus 3. So here's our initial position function. So when we have an initial velocity of 1 meter per second, it shows up here as the constant in our velocity expression. And then we have a starting position of 3 meters, and that shows up as a constant in our position equation. So at this point, our essential question, we've kind of moved away from our essential question, so we're not going to worry too much about that. And if you're in class, you will do a mean value theorem anchor chart as a class activity. But at this point, you should be able to do day 2 of the mean value theorem homework.